An inconsequential mess leverages Wwise and Unity to deliver a virtual reality prog rock experience. Although there was a ton of composition and production completed within Ableton Live 10 and Nuendo 11 to create thousands of musical modules, it's difficult to comprehend how all of these modules combined to create the final experience. This video aims to demystify this process by walking through the Wwise and Unity projects and demonstrating the musical effects of differing technological approaches. We'll first open the Unity project to familiarize the virtual environment upon which an inconsequential mess is based and discuss its interesting elements. Subsequently, we'll open up Wwise and listen to the resulting musical variations triggered by user choices within the finished built application. The virtual world of an inconsequential mess is mostly a sparse, desolate basement setting filled with polygon objects that play musical segments. These objects are split into core song objects, which act as the backing band or ensemble, and interactive objects. These are visually represented by a square and a sphere shape, respectively. Instead of placing these objects in the space manually, it was decided midway through development to automate the generation of these objects at startup and partially during runtime. Core song objects were instantiated at the start. This was due to synchronization issues that we'll discuss later, while interactive objects were not loaded or even positioned until the user walked through a specified trigger region. That same region would also randomize the core song object's instrumentation and whether or not they were muted by default to start with. This randomization ensured that no matter how predictable the song got through repeated listens, the same user can never replicate the experience twice. And it also generatively spatialized the experience by moving objects when the user re-entered a room. In many ways, this instantiation of objects during runtime allowed the experience to pull a much heavier weight in terms of randomization by leveraging user choice. Here is one of the rooms from the final experience, named, quite originally, Room 1. We can see the 4 physical walls of the space, surrounded by a larger blue cube, which is called Trigger. Now, this trigger is the boundary point at which a user initiates object instantiation when entering this zone. The component was never renamed after its intended codename of instantiation test, but this fully functioning component features a number of variables that can be set for each independent room. Firstly, the developer designates the prefab object for both an interactive object and a core song object. Furthermore, they can select whether or not this room should include either of them. In its present conception, we've chosen the only prefabs that were made for the experience. But variations could have been made whereby an interactive object was different room to room. Secondly, the developer needs to outline a boundary object. Now, this object is just a trigger collider that outlines the room's boundaries and enables the trigger object to instantiate objects within the confines of the room. This is denoted in this video as being a green cube. By allowing developers to choose this boundary, a trigger object with the instantiation test component attached can manipulate any boundary in the game. That includes areas that aren't confined to 4 physical, or we should say virtual, walls. So without any further manipulation, the objects would load within this room, but they could also be placed in front of a doorway. As such, the third step in this component is to designate pre-assigned positions, where an object cannot be placed. In this room, we placed a cube at each doorway and assigned them to the instantiation test component, and thus no objects would ever be placed within this space at any point during the game. Those cubes could have been designating where a sofa was or a table, and it's up to the developers to choose exactly what pre-assigned positions are necessary. Now let's dive into the instantiation test script itself. And this component has two primary functions. One, to instantiate objects within a room's boundary, and two, to delete interactive objects when the user leaves the space. Of course, core song objects were never deleted because they could not be loaded during runtime and only at the start of the game. To keep track of all of these objects, I used 3 dictionaries and 1 hash set, which recorded the objects that needed to be instantiated and also the ones that were already loaded. At start, each of these components would identify the name of their parent game object to enable clear naming conventions for each instantiated object and identify the bounds of the room's boundary object. Subsequently, the room was split into X and Z axes columns based on the size of the boundary and the space per object variable. In order to toss out any potential position that overlapped a pre-assigned position, like a doorway, a new position called new pos was created for every Z and X axis value with a randomly variated Y axis value. Then, if this new position was within a pre-assigned space, it would be added to an obstructions hash set. Subsequently, the combined hash set of potential positions would be used for instantiation, excluding any position included within the obstructions hash set. Using hash sets here is interesting in itself because by default, they do not allow repeated elements. So each possession vector included within either potential positions or obstructions is discrete. The component determines the maximum number of objects according to the number of potential positions, and the developer set fill percentage value. It also initializes the probability values that are required for randomization and triggers an internal function called update room objects. This function simply randomly selects a type of object to instantiate based on the parameters set by the developer for each room. And at this stage, since the core song objects have never been loaded, it adds both interactive and core song objects to their respective dictionaries. Notably, these have just identified the name and type of object to be instantiated, but has not loaded them itself. So, back to the start function. It now instantiates the core song object types, since these need to be operating at the experience's start due to the previously mentioned synchronization issues. First, it sets up a local list, posAssign, which includes all the vectors from potential positions. Then, a random index is loaded as the position value for each game object instantiation. For each key value pair within the core object to instantiate dictionary, the component loads the coreobj.value, which is the type of object prefab at the random position. Subsequently, the game object's name is changed to match the string from the key, which is the explicitly generated file name structure we outlined before. Finally, it removes that position from the posAssign list and repeats the process until the number of core song objects is reached. The component wraps up its starting process by updating the remaining potential positions for interactive objects and adjusting probability values and maximum object numbers to reflect the loaded objects. Now that the core objects are initialized in this room, the update room objects function will only deal with interactive objects when users enter a trigger zone. Now, there are only core song objects in the space, but this is because the interactive object type do not play synchronously and can be started by the user at any point in time. To increase variation, I decided to leverage this by deleting the interactive objects when a user leaves the trigger zone and only instantiating a random number of them each time the user returns. So a user can return to the same room, but the interactive objects will not be in the same place. This means that the instantiation process we saw before for core song objects happens on the onTriggerEnter function for interactive objects. Once they are instantiated, the loaded game objects are then added to the objects to destroy dictionary, which enables them to be destroyed when the user exits the trigger zone. To increase variation even more, the core song objects are variated at this time too, with their instrument being randomly selected each time. So while you may leave a space with 2 drum kits, you could come back to a strings and piano instrument. So how did this randomization happen at the room's boundary? Well, when a user entered each room proper, the audio state trigger component, which features 4 probability values that could be adjusted for each room, set the likelihood that a particular musical sequence would be triggered. We'll look at them in greater detail within Wwise later in this video, but for now, it's important to understand that there were 3 main musical sequences which featured differing orders and variations of verse and chorus modules. So now that we've seen how each object is loaded, let's take a deep dive into the object prefabs and how they operated. First up, let's focus on the core song objects. These objects acted as a rock band, with each object an independent musical instrument which combined to create an ensemble. The objects played synchronously, always playing the same song section and sectional variation, and this was triggered through users' movement through different rooms as previously highlighted. Each core song object visually comprised a cube and a surrounding halo of light, which is placed on a child game object. The color of the object changed dependent on the chosen instrument and would turn gray and have no light emitted whenever the object was muted. On top of the required Wwise components, all functionality for these objects was handled by the custom core song object controller component. In the editor, developers could choose a real-time player control to assign to 4 axes of movement for each controller. In all of the core song objects instantiated throughout gameplay, this means that a user could manipulate the volume, distortion, reverb, tremolo, filter, pitch shift, delay, and flanger effects on each individual core song object. Furthermore, a developer can choose which instruments are available. Each instrument in Wwise should have an independent switch value which can be mapped into the instruments array. Developers can then set the mute/unmute events for the object as well as controlling the lighting values for the object's halo. Lastly, the developer can set a color for each instrument type, whereby each index of the instrument colors array would be assigned to the same index instrument as outlined in the instruments array. The final options include a mute color, as well as a Boolean variable that denotes whether or not the instruments should randomly be muted when they're instantiated. So let's just take a closer look at this component. As soon as one of these core song objects are instantiated at startup, the instrument is randomly chosen and assigned with a 50-50 chance of being muted by default if the random mute on start Boolean is checked yes in the editor. Subsequently, this component is relatively simple in that it assigns the value of each axis of variation to the appropriate RTPC as chosen in the editor. Of course, the way this component finds variables like left x-axis is more complex, since it is dictated by the player's control, which is managed in the script interactive player controller. Now, there are a few functions that each core song object has available to players. Add instrument and subtract instrument allow the user to cycle through available instruments by consecutive indexes in increasing or decreasing values respectively. Also, the user can mute or unmute the object, which changes the color in this case, and halves or doubles the object's light intensity respectively. But of course, these manipulations of core song objects cannot be achieved without enabling specific controls for a user. The interactive player controller script handled all of these user actions. Focusing on core song object manipulations, a user's gaze, dictated by a vector originating at the VR headset's central camera position, would hit an object, and if its layer, set within the Unity editor, was core song objects, then it would initiate core song object manipulations. Simply, if your gaze drifts to a new object, it resets your selection. Otherwise, it starts a timer to ensure the user is focused on that object and not briefly moving their head past its position. Once selected, indicated by a halo light showing on the object, a user can manipulate its parameters by selecting the trigger and moving their controllers around. The initialize functions called when the trigger is pressed show a visual display of the current settings for the selected object. This comprises a large sphere indicating the range for each axis on each hand, and a small dot that indicates the current X, Y, and Z axes in space. Furthermore, the player's saved axis values will be made to equal that of the selected object and subsequently manipulate the selected object within the hand core song function. This function simply measured changes in axis values while the trigger is selected for each hand, and subsequently mapped these values between max and min and changed the selected object's parameters to equal the sum of the last value plus this change in value. These same values would also be sent to the dot indicator to ensure that the visual interface matched the current object's parameters. The final aspect of the core song objects that now needed to be managed was how to start all the objects together so that they were in sync at all times. As mentioned in the preface of this video and a few times afterwards, Wwise does an excellent job synchronizing musical elements together, but there's a catch that significantly impacted my approach to spatialization and synchronization in this piece. Each object needed to be spatialized independently. In other words, there may be two pianos playing in the same room, but they need to emit from two discrete positions in space and have independent audio effect parameters. To achieve this type of spatialization, Wwise has provided the AK ambient component for Unity3D projects, and we could choose large mode emission or multi-position emission to increase an object's spatialized audio. Unfortunately, the large mode works by emitting the same audio, so the same audio event, same audio effect parameters, across a larger space. And the multi-position mode emits the same audio event at multiple positions in the space. So both of these options provide valuable functionalities for this piece, but have one critical flaw. They both emit audio from a single event. Now, this means that the two piano scenario mentioned above would only work if the two pianos had exactly the same parameter variations, a feature I'm actively trying to avoid in this piece. So instead of using these modes, I used the simple mode, which emits a single audio event from a single game object. And while this solved the problem of having independent core song objects, it made the issue of synchronization difficult. By splitting the audio events across each object, they could not leverage the inbuilt synchronization tools built into Wwise. And I got around this by instantiating all of the core song objects at the start of runtime, and then triggering them all in the same frame on the manager script by calling a custom AK trigger component for Wwise. This component was called AK trigger core song and simply enabled the AK ambient script to trigger the chosen event when the component was called. As such, all of the core song objects started at the same time, and provided the sequences were explicitly scripted, they would never get out of sync. So let's move on to the interactive objects. And in many ways, the interactive objects share the same elements as the core song objects. They are based on a basic geometric prism They emit light when playing, and users can control parameters gesturally by moving their controllers in three-dimensional space. But there are some major differences in how they operate that set them apart from the core song objects. Interactive objects operate independently of one another and could be considered as soloists. The difference here is that they do not play synchronously through the same section as one another and only play if the user tells them to. Subsequently, these objects have been rigged to only start on the next beat of the core song. There's many ways to achieve this functionality and none of them were easy, but the way that I handled it, and made the most sense at the time, was to set up two main mechanisms within Unity3D, not Wwise. First, Unity needs to keep track of the beats of the core song, and two, any play event on the interactive object needs to wait until the next beat before starting. So we'll look at the manager script because this is where a lot of this work happens. And the first thing that I did was make a click track in Wwise, which actually has no audio. So it's not really a click track at all, but for naming convention, it made the most sense. What this does was keep in time with the quaver beat of the core song. So while the core song frequently changed time signatures, this click track maintained a steady 9 quaver pulse throughout. And by adding a callback to the click track event, any music sync supported by Wwise triggers a function called global sync callback. This function looks out for 3 main sync events from the core song. 1, beats, 2, bars, and 3, ends of phrases. But for the synchronization method we're talking about, we only really need the beat function. So every beat that the core song plays triggers the global sync callback function, is filtered out, and subsequently triggers the beat add function that simply adds to a count of beats. And by itself, this doesn't really achieve anything, but the interactive objects all look for this beat value on the manager script before they play. So let's go look at the script for that. When a user chooses to play an interactive object, they trigger the object admin function with a string play. If it's not already playing, the script waits until the next beat before triggering the play event, and this means the patterns start on the beat each time. But once they've started, the objects are free to phase in and out of sync with the quaver pulse according to the modules selected by user interaction. So how exactly does the interactive object respond to user input? I used the exact same controls as outlined in the core song object section of this video, but this time the left hand's axis manipulations directly controlled musical variation. Specifically, users can manipulate the object's phrase speed, pitch, reverb, and note density by using their left hand's X, Y, Z, and axis rotation respectively. Following that musical manipulation, users can also variate audio effect parameters with a low pass filter, high shelf equalization, delay, and tremolo effect all on the right hand. But with this Unity project outlined, I think it's time to hear the result of the combination of these efforts. Wwise provides comprehensive game audio functionalities within an intuitive UI that provides a familiar layout for musicians with experience in traditional digital audio workstations. The standout feature for this project, and the main reason for choosing Wwise over other alternatives, was the excellent interactive music hierarchy available. Of course, like anything in this area of research, it didn't quite work out how I had hoped. You see, the way I'd intended to operate this piece was to leverage the built-in synchronization of the interactive music hierarchy to keep all of my objects playing together. But, as we mentioned before, the program doesn't synchronize across separate game objects with independent positions in the virtual environment, because they need to be registered as separate events. So each event may be synchronized with itself, but not between events. Let's first take a look at the core song objects. After the loading screen phase ends, Unity triggers an event on all of the core song objects called play core song. Unsurprisingly, this event plays the switch container called core song, but with the sectional state of start menu. And this started a playlist of drone tracks that only emitted from objects with the drone instrument switch type. So in Unity, I didn't discuss the drone object types because it's not very interesting, but there are a couple of sections where I manually put core song objects in, but only with the instrument type of drone. Now, this drone playlist simply moves from a high climactic synth and lowers in pitch and intensity into a randomized oscillation between two fairly muted synth drone variations. Then, as a user walks into a different room, it would trigger one of the three sequences that dictate a unique musical playlist. These phrases only played on instruments that weren't a drone, and this made up that desired prog rock band ensemble we talked about earlier. So the sequences are not randomized. So to introduce the requisite variation, I made sure to occasionally randomize some sections. Now, the way this works is the instrument would play the same phrase of music, but it would randomly select which timbral variation. So a really simple example is instead of the strings playing long legato notes, they might play pizzicato. And that way, two string objects in the same room might be playing the exact same piece of music, the same section, perfectly in sync, but one has randomly chosen that legato phrase and the other is pizzicato. With such a scripted musical structure, the piece now leaned more on randomizing the user's choices. And as such, they could cycle through these instruments at any point in time and manipulate the ensemble that surrounds them in the room. Furthermore, I've attached several audio effect manipulations to these objects that the user can manipulate. For example, each instrument has a manipulatable filter, as well as more complicated effects like the pitch shift effect. These audio effects are manipulated by those RTPCs that we talked about earlier. So in the simplest form, the RTPCs simply map a GAM variable to an audio parameter. For example, the filter RTPC is linked to both a high pass and low pass filter with a value of 0 primarily playing low frequencies and a value of 100 playing high frequencies. But the pitch shift demonstrates a more complex audio effect mapping process. You see, this effect first requires an auxiliary bus that receives increased output from the core song object as the pitch shift RTPC increases. Now, this auxiliary bus features the actual pitch shift effect, which has a high pass filter frequency, which, as the RTPC increases, the filter opens from the top down, since the lower frequencies of this effect are undesirable. Lastly, the bus's volume needs to be turned down to compensate for the increased overall volume of the combination between this effects bus and the dry sound of the object itself. So the result of this effect is that you actually get a blend between the actual object's dry sound and the pitch shift effect, and that combined audio is the effect that we actually hear at the end. The final aspect of the core song object that requires special attention in this video is the key signature state. This is a crucial aspect of the core song objects, despite only manipulating the interactive objects. Since the core song modules are particularly chromatic, the key signature of the interactive objects needs to change appropriately. So to do this, an event that triggers a change in key signature state is placed on each core song module wherever necessary. And as these states change, you'll notice later in this video that the interactive object module changes to play the enharmonic equivalent notes. So this is a perfect time to move on to the interactive objects. The mechanism behind these objects is exactly the same, but there are some added functionalities because the users can directly manipulate musical variations. To achieve this, 3 RTPCs respectively map to pitch, speed, and note density. The way these work is slightly different to the RTPCs we just talked about because they actually map to a switch variable. As the user moves their controller and the pitch RTPC increases, what it does is it changes the RTPC, and at certain values and thresholds, the pitch switch will change. Then, with the pitch chosen and the switch container going to the correct musical module, the users can manipulate the speed and the phrase density of those modules. On top of these musical variations, the users have control over the instruments, just like the core song objects. So you can hear them as they cycle through. Every time we change this instrument, it will change accordingly at the same time in the same module. And lastly, these objects are going to change dependent on the key signature. So as the chord progressions change scale, each note in the interactive object is going to transition to the closest enharmonic equivalent. Now we've seen how the virtual environment and interactive audio was set up. How do they combine? Well, let's wrap up this video with a simultaneous capture of my input and the combined audiovisual response.